Thanks so much, Luis.
Okay, and you should be seeing my screen. So if you are not seeing, what obviously is my presentation, then just say something. Otherwise, I'm going to assume that everybody's can see the slides. And so, yeah, thank you. Thank you for the invitation. This is actually the first time I'm doing this type of presentation, so I'd be really happy if anyone has feedback now or later, because my point here is the why and the how. So I'll first try to explain, why I think this is useful, software testing, and then give a little bit of framework on how one can think about different types of tests, and maybe some of the discussion that was already happening could fit into this. So I'll start by saying that not all research code is equal, and often research code starts off as a one-off script. We're doing some sort of like, oh, can you check if the genomes have, what's the GC content? If it's, it's like a one throw off thing. You might even just be running it on the command line or the Jupyter notebook or whatever. And here, this doesn't need automated tests probably, and it's actually often wrong, to be frank. When we want to move the type of code that we publish in our group, there's actually two different types of code that we publish. So we have papers that we publish because they contain interesting biology, interesting ecology. And for those, we publish the analysis code as well. But the code there is secondary to the main results. So the code there is a form of extending the methods. So, so that where we expect that most users will not be interested in the code themselves. And here, I actually think that, adding tests can be useful, but it's not necessary. If that code it doesn't have, this automated testing, then, I'm not gonna say you should be doing it. But we also publish code that is packaged as a tool. And so in that case, it's different, because in that case, the whole purpose is that other people use it. And it's for this code that I think that tests are essential, because especially for tools that we are going to publish and they're going to be living for a long time, that are going to be, they're going to be active for many years, and we commit to supporting our tools for 5 years at least after publication, and many of them have, now getting longer than that. And so the tools that have been mentioned in the hackathon, they all fall into this, these are tools that others are going to use. This is not going to be a single paper. If it's a successful tool, it will be hundreds, even thousands of manuscripts will be using it. And so it's this where, this is the setting that I think, that tests are really important. And so tests are kind of a form of communication. So they're a form of communication between people who participate in the project, between the different, and across time, so, you've probably all heard this saying, that yourself from 6 months ago is the worst possible collaborator, because who knows what that guy was thinking, and, and he doesn't answer emails. So yes, so whatever code I wrote 6 months ago, I mean, whatever that guy had in his mind, I probably don't remember it anymore. But if Luis from 6 months ago actually wrote down a test, then that's a form of communicating with me. And also, in academic science, often groups are transient, means people, students move on. We want them to move on. We want them to graduate. Postdocs move on. People change, and so everything is in flux. And often, if a student moves on and if they left a tool that the group must support, then having a test suite really does help communicate, and because it forms this this communication, this form of active documentation. Because it's easy for me to sort of give you a high-level description of what the piece of code does, but if there's an exact task, then that's very precise. It makes it easier to change the code. It also often makes it easier to jump into code. I've experienced this where, because often as part of a test suite, maybe there's some test data as well associated with it. So if I want to test, if I want to do a little change, I can see how the parts fit together. And so that's often again, just makes it easier to work with the code. And this was, I was saying, it's personnel turnover, it's a huge issue. And so it's much better if a student leaves and they've left behind a tool, if they've left a comprehensive test suite. And here comprehensive can mean slightly different things. There are actually tools that can check for that, that can check if every line of code in your software is being tested, or if 90% or 50%, and that's one way of defining comprehensive. And they can help with making, sometimes what you don't want to happen is you're working on some piece of code and somehow you change a little thing here and that causes changes in some other parts of the code. And so what testing gives you is, that's at least, that won't happen implicitly. And then, finally, it's very easy to fall into that trap where, here I'm working on my machine, I run Linux, I run Python 3.7.5, and I write something that somehow doesn't work on Python 3.5 when it's running on Mac OS. And to try to figure those things out by hand, and it's basically a huge amount of work that nobody ever does. But if you're using, say, GitHub Actions, that's just one more line there where you say, please test all of these different Python versions and test all of these different operating systems. And so at least then you get all of these extra platforms with no more effort. And then finally, the end result that we hope for is that we end up with fewer bugs. I'll also want to make the point that sometimes I do get a bit of pushback with people saying, oh, look, all of this stuff, it's great for, if you're a software developer, but in science, we don't care so much if the code is good or bad, as long as, what we care about is that, is that we got our biology, we learn our biology, we learn our microbial ecology, what the code actually does, this is not that important. And I actually think it's, in some ways, that's the other way around, because in biology or in science in general, we do care about methods. So it's not, it's not enough to say, oh, look, here's a pretty plot. We really do want to be sure that, whatever's behind that pretty plot is what we think it is. So whatever is behind the analysis we're presenting really is what we think it is. And it's not enough to say, oh, look, but the results look good. I mean, if you're developing some sort of web platform and it looks pretty and customers are happy and they're paying you money, at that point, really, if your code's a mess and you don't really know how it works, I mean, that's can be okay. I mean, if everyone's happy, but in science, that's actually not okay. So if if I ask, oh, this is great, how does this analysis work? And you say, well, we don't really know, but some student left some code and it does pretty pictures. Yeah, that shouldn't really, that's not okay. So we do want to be confident that our software really is giving us what we want. And again, mostly when we're discussing tools that are used not in a single project, but across many projects. And you've probably now seen that there's a fair amount of boilerplate when we're doing automated testing. We probably have figured out how you have to set this thing on GitHub Actions, and you have to figure out how to set up unit test framework, PyTest or whatever you're using. And this is an initial barrier, but once it's done, it's basically done. So you do it one time, and then it was going to work for years. As long as GitHub is there, which might be, a few centuries, once you've set up this framework, everything is there. Because the truth is that everyone tests their code. Like everyone, everyone tests their code. The question is, do they test it, in a systematic way? Because, the more typical, development is that, you start by, you write code, then maybe you compile it, depends on what programming language you're using. And then you kind of run it on the command line or on the notebook or whatever, and you see if it works. Maybe you're a better programmer, and so everything works the first time you run it. If it's me, it's probably not working, so I go to one, and then write more code, fix it, and then I keep iterating on this until eventually I'm happy, and then I add it to the repository. So the only thing I'm gonna ask that people start doing more is that, here you add this one extra step, where you take whatever the code, whatever these tests you're already doing in step 3, where you were just informally testing your code, because everybody does test their code, and you take that tiny extra bit of effort to save it as a test in your, as a file, as a script that can be run, and you add that to your Git commit, and then GitHub Actions will run it for every other commit forever. And so the amount of extra effort, once you've gotten through this original barrier of activation, of having to set up GitHub Actions, having to learn all of this stuff, then on a day-to-day basis, it's very little extra effort. And because it does end up saving you from making mistakes later down the road, overall, for a long-lived project, this ends up saving a tremendous amount of time. So tests are good. Now what I want to present is an attempt to try to categorize, different types of tests. This is a little bit informal, a little bit work in progress, and it's not comprehensive, so it's not gonna. But this, I think, this would be also the main terms that you or the main concepts that you want to have in mind. So in the first question, the first sort of axis is, how much do you peek inside your tool? And here we can talk about, sort of white box testing, and sometimes people use the term unit testing to refer to any kind of testing, but maybe more precisely, this is unit testing. So you're testing when you test individual parts of the machine. So you test individual functions or individual classes in your overall tool. And then the other type of testing is black box testing. And here there's different names, and there's a bit of nuance between this, but basically you want to not run individual modules, but bigger parts, including just the whole tool as a whole. And let's just first look at white box testing. So and here I'm going to show an example, and most of my examples, actually all but the next one, are in Python, using PyTest, but this really shouldn't. But all of the concepts are more generic. And Python is pretty good at being kind of readable. So in this case, I am testing this function called hash1, and I'm testing how it works with the NumPy array. And this happens to come from a bigger tool that we have that's called Jug. But this test really just focuses on this one hash1 function. So this type of unit test is actually, it's pretty well supported by tools. So there's a lot of support for unit testing. It's really good because if there's a problem with this test, then I know that it's the hash1 function. So if I somehow introduce a problem and this test starts failing, then it's probably the hash1 function that's wrong. And often this type of unit tests can be produced as as you're debugging. So if you have some sort of bug in the code, often you might suspect, oh, maybe it's the hash1 function that's wrong, and it's very easy to then produce a test, and either one, you're right, and hash1 function is wrong, and you've produced a test that fails, and now you know what you need to go fix it, or actually the hash1 function is working as it is, but you can still save that test, so that you keep enhancing your test suite as a side product of debugging. And again, it's probably something you're already doing if you're working with code on a day-to-day basis whenever you have a bug. And this is just them saying, instead of just testing this stuff one time on the command line and then that being lost, you can save it as a test. The main disadvantage of this type of testing is that it needs to be rewritten. If it's very dependent on the internal workings of the tool. So whenever something changes, the test is no longer relevant. At the other extreme, we have this black box testing, and actually maybe I'm going to show you an example. Let's see if this works. All right, let's see if okay. So this is another example this is another tool. Okay. Yeah, this is a tool we have called NGS, and we have this test subdirectories, and then inside it, as you can see, we have a bunch of these further subdirectories, and we have a little bit of infrastructure. I'm just going to pick one, and each of these subdirectories has a couple of files, and there's the convention is that some files are called expected.something, and then once if this is this .ngl file specifies what the tool should do, and the tool is going to produce a file called output.fq, and then the testing system compares output.fq with expected.fq, and as long as the output is equal to the expected, then that's a successful test. And so that's sort of at the other extreme of the unit test that I showed before, so we're testing the tool as a whole. We can test multiple things at once, including all of their interactions. Whereas previously we often could get those, almost for free as part of debugging. Here we often get them almost for free as part of a bug report, because if a user says, oh, I tried this and it's not working correctly, then often that's that can easily be turned into a test. And a big advantage is that you can change the code internally and improve it. I mean, you could rewrite the whole thing in Rust, and be sort of hip about that seems to be the hip thing to do nowadays, and all of the test suite would still be valid. So if you rewrote it in Rust and it passed the test suite, then then users could keep using it without even noticing. There's some disadvantages, some trade-offs here. So here every time you're running, you're running the full program. So this can take more time to run. I mean, all of our tests are kind of toy examples. So they, but it still takes several minutes to run the whole thing, as opposed to a few seconds for the more typical unit test. And it's less informative when they fail. So if we introduce some sort of bug, it's not as clear, oh, we know this is failing, but we don't know exactly where. Let me just see if we don't know exactly where. And unfortunately, it's not as well supported by tools either. So that's it. So those are the trade-offs. I mean, just trade-offs. Okay, so that was the first sort of axis of that. I went, like, are we checking? Just checking the chat.
Hey Pedro, Luis, I'm sorry about that. If you want to hear questions, I'll read them out to you as they go, but I just assumed maybe you'd want to hear them at the end.
It's fine. I was actually afraid that my sharing was failing, because they got one of these, your connection is unstable messages from Zoom.
Oh.
I was like,
You're great so far. You're getting some questions, but it's your choice if you want to save them for the end.
I'll save them from the end because I think yeah, I'll save them from the end.
All right.
Okay, so another axis of testing is kind of what are you testing, and so one type of test, and I think this was being discussed before, is this called smoke test, and so this actually comes from the construction industry. So a smoke test, and I've heard of two different types of smoke tests. One is you put smoke in your pipes, your physical pipes, and then you see if there's smoke coming out of the walls. And if there's smoke coming out of the walls when you put smoke in your pipes, that's actually really bad because that means your pipes are leaking. And the other type of smoke test is you fill your house with smoke, you close the windows, and then you see if the smoke is leaving the house. That would mean that again you have a leak. So this is a way of testing for leaks, but you really only have smoking coming out of the out of your walls if you have a huge hole in your pipe. So if you have a tiny leak, a smoke test is not going to catch it. If you have a huge hole in your pipe, then your smoke test is going to catch it. So this is the construction industry version of a smoke test. The software industry version of a smoke test is basically you check, does it run and does it seem to return something? So again, it catches really gross bugs or really gross errors, but it's really shallow. So here's an example. Again, this #1 function, and we're just giving it some random dictionary, and then all we check is that it returns something that was not empty, and that's it. And basically, if it doesn't crash and it returns something, then this test passes. So this is a smoke test. It's often the first type of test you want to you write because it's the simplest. And again, if your code doesn't pass this type of test, then you have a huge problem. A slightly more advanced test is where you just test the basic usage. So here again, you have two functions, decode, encode, and they should be sort of the mirror of each other, the reciprocal of each other, and it's just basically testing the basic functionality of this pair of functions. Another type of test, and here is often we want to test corner cases, like weird stuff, and here I have this example that's actually also an example of what's called a regression test. So a regression test is what I mentioned before, where when you find a bug, then you turn it into a test. And so in this case, someone apparently reported a bug, issue 39, and this was a weird case, probably trying to encode the empty string. And empty strings, just the sequence that's just A, those kind of weird stuff. That's often edge cases, corner cases. That's often where bugs are hiding. So trying to test for those explicitly, it's a good idea. And regression tests are also a good idea. They're a good idea both as part of the development process. So when someone it's often a bug report, you have to work a little bit through it, or get a bug report from a user, or or from yourself. You have to work a little bit through it, and as I was saying, often as part of the debugging process, you can easily end up generating tests. But the other thing is, so if you have a bug, that means that someone, maybe yourself, made a mistake. And normally people make mistakes because the logic there is, you're kind of in a tricky spot in the logic. And so if you made that mistake one time, you're likely to make it again, or someone else is likely to make it again. So it's more likely than random that the same bug will reappear. And so if you have a regression test, at least you make sure that the next time you make the exact same mistake, it will be caught immediately by GitHub Actions. so the final sort of division that I want to talk about is, okay, so we've talked about, what level you're testing, and now, how do you test, so just some basic techniques of testing. And the first one, and this is kind of like the equivalent to, doing controls in a wet lab experiment, right? Where you have a positive control and a negative control, and you know what you want to see for those. And so you just run your code on something, and you know what you want to see. So here, you know that this function should, if you give it a value 2, should return 2. And some very simple examples maybe you can do in your head, or maybe you just can work out the math by paper or something, and so you can check a known case. But sometimes another way is you can check against another way of doing the same thing. And so when which might seem a bit absurd, are you asking me to write the code twice and then check if I get the same result? And actually, I kind of am. But let me give you an example, and I'll come back to this example later. This is also actual code that we have. So what we want to do here is, I'm going to elide the details a bit, but let's say you have this sequence, and we want to work with k-mers of size 5. So we want to take the first k-mer, and we want to compute the little hash of this k-mer. And then we want to take the second k-mer, and we want to compute the second hash of this one. And then we want to take the third k-mer, and so on and so on. There's 2 ways of doing this, or at least 2 ways. The simple one is we take the first bit and we compute the k-mer code, and then we take the second one and we do this independently. And this is what we do here. So we compute 1 k-mer. Okay, this is a little bit Python heavy if you haven't seen it, but we are going, position by position and taking that substring and then calling compute k-mer 1 k-mer function. This is actually quite inefficient because we can actually compute the next k-mer based on the previous one. But doing that, computing all the k-mers, it's much faster, but it's actually tricky. The code there actually had a really tricky bug for quite a long time. But so here what we can do is we can use both versions and then check that, at least on this example, that they return exactly the same thing. Another typical case is, in many problems, you can easily do a brute force solution, just check every possible combination of inputs. And this is generally a terrible idea because it's not going to run in usable time. But, but for testing, maybe you test it in a small data set, and it works. And you can then you can use that brute force version on a small test set and check that it returns the same thing as the real code. So this one particular variation of this is to compare against the previous version of the code. And I've seen that sometimes this is called regression testing, although I think the other use of the term is the more common one. But here the idea is you have a version of the code that you're pretty comfortable with, or at least it's the version that you've been using. And so, and you can, now, but for some reason you want to improve it. Maybe, maybe it's not fast enough. Maybe there's a new, maybe it's, there's a new fancy algorithm that you want to implement something. So here you can use this previous version of the code either to generate test data, and then you can check against these, use this sort of known case approach or you can keep this, or you can keep both versions, one that you just use for testing, and this new version, that's better, faster, shinier, whatever, that you use for real data. And so this is a special case of the previous, but it comes up quite often when you want to improve it. You can use this to, at the very least, make sure that you're not introducing any change without inadvertently. So sometimes you do want to make the changes, but you don't want them to sneak up on you. You want that to be a choice and not something that, just because you fixed something here, something changed over there. Okay, so this would be, I think, the main techniques or approaches that we would want to take for testing. But one thing that once you've started working with tests a lot is that you start to notice that even when you're writing the code, so before I said, you write the code and then and then you do tests and then you check that the tests work. So that's there's another approach. This is I wouldn't say it's very popular, but there has maybe very dedicated proponents of it, which is called test-driven development, which says, oh, you should write the tests first, write the tests and then write the code. But you should be aware of that. Some people really say it works for them. So maybe it works for you. Personally, it actually doesn't really work for me, but it's something to be aware of. But one thing that's actually I noticed in myself is that when I started to make my code more testable. So here, just give a couple an example where, so the best functions to test is pure functions. So functions that just take some arguments, do some computation based on those arguments, and then return some values. No fancy global variables, no and you try to and one particular way of doing this that actually comes up quite often, for example, is that a function that takes a file name is not so easy to test. So for example, you can take a function like this that takes in a file name, and you can easily transform it to take a file object, and now you can still use it in the same way, but when you're testing, instead of passing at an actual file, you can pass in a pseudo file. And in Python you have string IO and bytes IO, but all of the major programming languages will have some sort of facilities to use this type of little tricks to make this easier to test, so that in practice, in the actual code, this function will be working with a file, but when you're testing, you can work with a fake file, and there's a lot of there's this generally we call something like mocking, where you're not really you can work with databases where you have fake databases, so you can make this maybe you can make this more advanced in that way. And then one important thing is you need to test for failures too. A lot of tools work well but fail badly. So meaning that when they work, but if they have if something is a little off, then maybe they don't do good input validation, or they don't. So again, a lot of the tools will have some support for here, for example, this is a PyTest example where you can check that some code is raising some exception, so that you can check, yes, this code should fail, and or in the example I showed before, where I was showing that we have this test suite based on sort of a black box approach. So it's a bit slow. Maybe if you were quick, you could have seen that some of the tests are called error tests, and there the purpose is the test passes if the code doesn't run. So if the program reports an error, then the test passes. So it's sort of and typically those would be some sort of the input is bad, the user specified some sort of mistake, and I'm sorry, this is a bit slow, but okay, but believe me when I say it, yes, we test for errors as well. So we have this error, that sort of have to, that the validation is working correctly somehow. So, right. Okay, so some things are inherently hard to test. And so floating point numbers are one you should be aware of. And there's two things that are really difficult. So one is there's this weird thing that's called not a number. And it's just weird. And this is what you get when you divide 0 by 0, or when when you take the logarithm of a negative number or something like that. And one of the weird things is that not a number is not equal to not a number. Yeah, so it doesn't compare equal to itself. And in fact, equality is really strange with floating point numbers because, so, if this is sort of, grade 6th grade or 4th grade math, A times C plus B times C, if these were real numbers, it would be equals to A plus B times C. But in floating point numbers, it's not, because the approximation is slightly different. And so this can change. And so often, almost all of the libraries will have some sort of facility to test for, is this close enough? So in NumPy, there's a function literally called all close, where you can compare if two results are close enough. It's not really, and it's normally good enough to do it that way. Code that's non-deterministic is hard to test. And actually, I was discussing, because I was preparing this and yesterday on Twitter, and someone said, how do you even test if code is deterministic? So that's like really hard to test. How do you test code that's supposed to give you the same result? If you run it multiple times, how do you even test that? And then also code that runs for a long time is really also hard to test. So actually I don't really have a good solution for this one as well. So I'll mention one last thing, maybe sort of an advanced testing kind of thing. So sometimes you'll hear this being referred to as quick check, because quick check was this library that introduced this concept about 20 years ago in Haskell. But as many of these things, nowadays there's a lot of libraries for this, and so all the major programming languages have a quick check equivalent. So let me go back to this example that we had before. I said, if I take this string and I compute the k-mers, and I can compute them in this slow way, or I can compute them in this fast way, and it should be the same. And I said, I have this string, but this string was literally me typing on the slides this thing, ATC-NGS randomly, because this string doesn't matter what the string is, right? This should be true for any string. And so here I could replace this by any random sequence, and this should be working, because what I'm testing here, and this is what property means, what I'm testing here is sort of a more abstract property of not of that particular sequence, but of any sequence. And here there's actually this hypothesis library that gives me the ability to do this, where I can say here I want text with the alphabet ATCG with this minimum size and max size, and then it's going to give me different sequences with this. And this is actually what the code looks like. The previous one I just prepared for the slides, but this is what property testing means. And so if you read often the theory seems very, seems a little bit abstract. And actually anything that comes from Haskell, often that community has a tendency to present things as very abstract. But in practice, this is what it means. It means you're testing something that should be true for any random sequence or any random number or any random string. And actually what's really great about these libraries is that they don't just give you random examples. So hypothesis has all of these heuristics where it's going to give you weird stuff. It's going to give you the string of all A's. It's going to give you the string that's all A's and the T at the end. It's going to give you, the strings that are as long as you ask them. And the other really cool stuff it does what's called shrinking, where if it finds an error, it tries to find you the smallest possible example of that still. So if it finds an error with a string of size 1,000, it's then going to, again, heuristically try to narrow that down to the smallest possible string that still gives you the error. So these are actually really powerful techniques. And so this is called property testing. Sometimes you'll see quick check being referred. All right, so, oops, sorry, skipped a bit too fast. Yeah. So this is the sort of the taxonomy. I'll post this on the Discord as well. So this is not an exhaustive list, but I hope it helps you a little bit to think and to discuss and to have some terminology. Now that over the first day, you've hopefully passed this initial barrier of all of the boilerplate and fighting with GitHub Actions. So this initial split between, are you looking inside the box, or are you just looking, are you just testing inputs, outputs? What kind of testing are you doing? Just really basic, does it fail miserably, or we're trying to hit all of the edge cases? And then some of these basic techniques of, just checking with actual cases that you can do somehow, sort of like controls in the wet lab, checking against other implementations, or this sort of property checking, which is actually really, really useful. And these libraries are actually really powerful, and they are actually spooky in how they find these really weird stuff. Okay, so to summarize, so everything I've said, I'm most insistent on stuff that's the tool that will be used by many, as opposed to, I think that code that's used in a single manuscript, we should still be publishing it as sort of extended methods, but it's okay if it's not tested as intensively. And the second point is I think everybody tests their code. I mean, you might not do it in a systematic way, everyone, but everyone tests it. And once you get past this initial boilerplate, it takes really very little effort to just turn the testing that you're already doing into something that can fit the framework. And then at that point, you can reap the benefits. So with that, I want to just thank you. And this was the first time I've been presenting some of this idea, so I'm very happy to get feedback. And I actually see that there's some discussion in the chat, so maybe I can address some of those. Okay, so Ines asks, isn't the idea to have both types of tests? Yes. Yes, you should have both types of tests. And we do both. I mean, our tools use both types of tests. I mean, yes, I mean, they test and they're complementary in many ways. And sometimes there's things where you can choose to do one or the other, and then I don't really say one is superior. Okay, I might have to switch to using my phone because if my computer freaks out, but I'm happy to take questions because I'm running should have brought a charger. Yes, I will post the little taxonomy box. I will post that on the Discord channel. I just need to. Yeah, thank you. Yep, go ahead.
Luis, thank you for this talk. I was going to to just say thanks for an incredible talk, which I think everyone learned a lot from it, and it's nice to get such a systematic overview of testing and what is possible. So I think if there are any more questions, you can also unmute and we can have a discussion if people like. Yeah, Lee's just saying that he's busy now with his 5-year-old. So he had a question: could you discuss how you test software with a random element to it? Like if I were testing the shove command, the bash command.
Yeah, that's really hard. I mean, that is kind of hard. So there are techniques. There are sort of very advanced techniques to do that. There's so yes, so the shuffle one is probably hard. You can probably test some of the internal stuff. So you can test if you have the same, if you have the same seed. By fixing the seed, you can test that some of that works. But testing the shuffle, I mean, testing whether shuffle really is random, that's kind of, yeah, that's hard. Then there are some techniques. There's something called metamorphic, where you can test, so if you change some things, other things change. I mean, there's properties of shuff that you could test. So for example, if you give it a file with 7 lines, it should give you the same 7 lines back. So you could check that it's not, for example, losing lines or repeating lines. So you could check that. You could check that, that whatever. So if you want to phrase it as type of a property test, whatever the input is and the output, the sorted version should be the same. They should have the same number of lines. So you could check those kind of properties, for example.
Great. Yeah. I also had a question. I also had a question about, because I really like the hypothesis library. That seems like a really useful thing. And do you know if there's anything that they have with like bioinformatics formats, because they are quite a general library, or do you know something that's similar to that? I think there's been discussion on the Slack as well before on that.
No, I don't. I mean, you could. I guess you could use it to. I mean, I think in their parlance to do it a strategy. So we use it there. Actually, that example I showed you, the final version is actually code that we use. So where we're generating, we're generating strings of ATCGs as a way to have nucleotides. But yeah, you could plug that in and generate a FASTA file by generating a random header. Yeah, and you could turn that into a FASTA file generator. So you'd have I think, yeah, in hypothesis parlance, yes, I think that's called a strategy. And you can have your own strategies. Yeah.
Okay, thank you. Then there's a question from Sam. Hearing all these interesting methods of testing makes me want to try some for myself. Do you have any pointers as to where to start? I just learned a bit of PyTest and GitHub Actions a few weeks ago. Is that enough for all those types of tests?
Yes. I mean, so yeah, so the only thing that I think with PyTest is maybe not, so this sort of very black box testing, we actually do it outside of PyTest. So as Inez was saying, we often our tools do have both. And so but GitHub Actions, I mean, basically GitHub Actions, you can run whatever you want. So, right, you can do whatever you want. It's very flexible. PyTest, GitHub Actions, and then maybe you want to just run your tool and see, and for that we actually use a couple of bash scripts, but it fits GitHub Actions without a problem. Where we're running our tool on, this sort of more black box testing, we installed it because we want to see that the tool installs on a fresh environment and then works correctly. Yeah. Okay. Yeah. Justin also likes hypothesis. Yes, hypothesis is actually really good. I knew quick check before from Pascal, but hypothesis is actually really, and it's spookingly good at finding these. Like it did find a corner case in that code that was, if you give it a string of A's and a G at the end, it would actually, that would fail. But you had to have enough A's. You had to have at least 31 A's in a row and then a G, and somehow that was related to the overflow of 64-bit. Yeah, it was weird, but it found it spookily. Yeah. Okay, I mean, I think we're also kind of out of time. So as I said, I just need to stop the sharing, and I can post that little diagram on the Discord server as well for anyone who wants. Yeah, and if people want to reach out and tell me more later, that will be fine. Just just email me. Okay, and any final questions, or I mean, anyone want to?
I don't see any questions now. I don't know. Yeah, and otherwise, Luis will be. I mean, it's 11 p.m. Right now for you, right? So.
Yes, it's 11 p.m. So I'm gonna take a taxi home. So
Very
sorry,
good.
guys.
Yeah. A lot of thanks that you agreed to give a keynote here, and I think we learned a lot, and it's been a pleasure. So thank you from also from Lee, who is muted now. Oh yeah.
Yeah, and thank you very much. My 5-year-old was jumping all over me and talking with me, but he has left me now. Thank you so much. I realize how late it is over there, and it was a great talk, and I learned so much because I didn't even know that we were doing black box instead of unit testing, and that sounds so appropriate. And it's almost like the blind leading the blind here, and I think your perspective was incredibly useful.
Okay, thanks. I mean, yeah, I actually enjoyed having to put the thought into how to present these things. So that was also useful for me. Yeah. All right, thank you.
Have a great night.
Thank you.
All right, I'll stop recording.